Should I start?
Yeah.
Okay. So welcome back, everybody. So today we'll discuss applications of the central limit theorem. So recall what we did yesterday. If x1, x2 are independent, identically distributed random variables, actually there was an important word, they were continuous random variables, because I was using the theory of the convolution for the density functions. So they were continuous random variables with mean 0 and variance 1. Then the quantity S1, Sn equal to x1 plus x2 dot 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 xn. If this is the case, then Sn divided by square root of n is normally distributed. That was what we proved yesterday. And it was a tour de force of Fourier analysis, using this essentially everything in the book, the theory of Fourier transforms. And I wanted now to make a few remarks with respect to extending this theorem to discrete random variables. But before I do that, let me remove any reservation about whether these are really serious restrictions or not. If we have x1, x2, dot dot dot, which are independent, identically distributed, with mean mu and variance sigma squared, then the random variables xi minus mu divided by sigma, these random variables, let's call these yi's, have mean 0 and variance 1. So we can apply our theorem deduce that if Sn equals, then Sn minus n mu divided by square root of n sigma. This quantity now is normally distributed. Okay, so we just removed the fact that there's no restriction really in assuming mean 0 and variance 1, because we can always retrieve the general case from that case. the calculations, the computational elegance which you have when you have mean, zero, and variance one, simplifies the discussion. It suffices to deal with those cases. That's point number one.
Yes, and this sum of YAs.
Oh, sum of,
YAs?
no, sum of the exercise, it's some of the exercise.
Oh,
I've
okay.
already, I'm sorry, I should have used, yes, I used as x's here, I used the same x's there, but now in general, if you have this, you just renormalize things. Okay, as I said, I'm not here to give you a course in probability theory, but I'm here to acquaint you with all the ideas so that it makes for reading independently on your own. With interest, you can read it because you now know where the subject is going instead of having a dry treatment of it. So now the question is, what happens if I have discrete random variables instead of continuous? So what about the case of discrete random variables? Well, in this case, there's a general methodology, and this methodology could have also been used to prove the central limit theorem. And this methodology has to do with what are called characteristic functions. So let me explain this. We will use the theory of characteristic functions. So given a random variable, x, we define a characteristic function to be the expectation of e to the I t x. Now what is that, okay? Which is, what's the definition of this thing? Basically, it will be, and if I, well, it depends. So if, let's just leave it like this for the time being, okay? It's just this is the function. So what is this? In the continuous case, e I t, oops, e to the I t x equals the expectation of this quantity. And I ask myself, when does this random variable take on the value u? It'll be e to the I t u, and the density is f of u, exactly. So you have e to the I t u, and the density function du. So in the continuous random variable case, the characteristic function is nothing but the Fourier transform. Yeah, exactly, with a small change in the sign there. In the discrete case, well, I'm going to take the situation, the discrete thing, as the values taken as the integers, let's say. Then I will have e to the I t x to be summation k over the integers times e to the I t k, probability that x equals k. So this is the expectation of this in the discrete case, where I'm assuming that the values are the integers. And so this is now recognized as, remember we said P of x equals k is the a sub k, the probability that x equals k, so you have these numbers summation a k equals 1, right? So we have a Fourier series. You can attach a Fourier series. So this is, in this case, Fourier series, case is continuous case of Fourier transform. And so both of these theories of Fourier series and Fourier transforms are nicely combined in the theory of the characteristic function. Now suppose, so this way, whether I have a continuous random variable or a discrete random variable, I can always talk about the characteristic function of the random variable. So now, given independent identically distributed random variables x1, x2, dot, we can consider let me point out these random variables with mean 0 and variance 1. So we can consider Sn, which would be x1, x2, xn divided by square root, like we did last time. Okay, we can consider that. And then the claim is the characteristic function. So my notation is, you give me a random variable, phi of that is the characteristic function. Then phi of S sub n of t goes to phi of the normal distribution. So the phi is the normal distribution. But what is this phi? What is the characteristic function of the normal distribution? Well, it's a continuous normal distribution, it's a continuous distribution. Therefore we go to this formula. Okay. Infinity. RT 1 over root 2 pi. E to the minus u squared over 2 u. Hey, it's the Fourier transform of e to the minus u squared over 2. The calculation we did yesterday. Yeah. It's itself. Hmm?
Do we have a minus?
Where?
Because the u is a minus u there.
Yeah, but it wouldn't matter. It wouldn't matter. Yeah, there's a minus, that's true. But no, it wouldn't matter. See, yeah, if that's what you're worried about. Minus t squared is t squared.
Okay. You can put ts minus t.
No, that would ruin all theology. Okay?
In the proof of central limit theorem, this we have proved, right? This convolution of this, that is the Fourier transform.
But no, we calculated the Fourier transform of the normal distribution in that context, and I'm just using it from yesterday.
No, I am asking that in terms of characteristic function you have written, that thing was the strategy to prove that the central limit theorem.
No, the strategy was to use theory of convolutions. Here I'm going to use the theory of characteristic functions. So I haven't proved this yet. I haven't. So if that's what's worrying you, I haven't proved this yet. To be proved. So just that maybe I should have said theorem here or something. Theorem, right? You give me independent, identically distributed random variables, mean 0 and variance 1. I form this object. The characteristic function of this object tends to the characteristic function of the normal. Sounds like a central limit theorem, but it's not. It's with characteristic functions. And this is much easier to show. I'll show it in a second. Okay? Much easier to show than the central limit theorem. It looks like the central limit theorem, but it's not. It's almost a central limit theorem, but I'm passing through these characteristic functions. Does it make sense?
What we did yesterday was to show that the Fourier transform that is converging to the exponential of minus t square. Isn't that the same thing that?
Yes, but this is now, and yes, I agree. It will, in the case of the continuous random variables, it slowly, it will work out to basically the same thing. But in the case of the discrete thing, this is a new thing. Because in the discrete thing, I've moved to a function, and I'm now talking about this characteristic function, these characteristic functions tending to that. Okay? Yes, you're absolutely right. You can deduce the central limit theorem from this kind of reasoning too. You can, but you have to do some. You could take the root of characteristic functions, which some books do.
Yeah, another question. This is for every t or.
Yeah, always. It's almost almost everywhere. Yeah, but here it's for every t. Yeah. I'm not going to be picky about that. So this is the definition. So what do we have to do? We have to check proof. We calculate the characteristic function Sn of t equals the expectation of e to the I t of, I'm sorry, this is, if you were trying to do it in tech, it's a mess. This is the nice thing about the blackboard. There are some advantages with the blackboard lectures versus the PowerPoint thing, because trying to do these things again, you have to type them. So, as you can see, this is e of I t x1 over root n, e of I t x2 over root n, dot e of I t xn over root n. If two random variables x and y are independent, the expectation of xy is equal to the expectation of x times the expectation of y. So if x and y are independent, the expectation thing is a multiplicative function. So this becomes product k going from 1 to n, expectation of e to the I t xk over root n, since the xi's are independent.
The xi's are independent, this means the function of xi will also be independent.
Pardon me?
So xi's are independent,
Mm.
then e to the power I t x1 by root n is also independent. I mean, in that way you are telling function of xi is also independent.
Yeah. That's the whole point. What does it mean for independent? The two things have nothing to do with each other, right? The probability of this happening intersect the probability of the other thing happening is a product of the probabilities. So one could write it all out and then do it, but it's more or less the same. Yeah. See this? The point is, this is why I say, I mean, as I tell you, when I was an undergraduate, I thought probability theory is chapter in measure theory. And I think I thought that way for a long time. Later on, I realized that this terminology, independence, statistical independence, random variables, why do they call it a measurable function? Why? All of this terminology is helpful, because when you say independent, it's like this coin tossing thing, you see, that's where the term came. The first coin toss was independent of the second coin toss. So this statistical independence is essentially that, and that's the way you should think about it. It has nothing to do with each other, therefore it multiplies. Something that multiplicative functions are always in number theory. There's an independence. Primes, independent. Okay, now the expectation of e to the I t xk over root n is what? It's equal to, well, this is the characteristic function of xk of t. Equal. And now we'll play the Taylor series game. Let's look at the Taylor series of this. Well, the first term is going to be 1, because? Oh, t by root n, thank you. T by root n. So, at 0, the expectation of 1, the density is 1. See, that's just the integration over the whole space. And that probability measure is 1, right? The first term is 1. The next term is, if you look at it, or you could have taken the power series of this thing, it'll be the mean value. But the mean value is 0. Should I do it? So this is equal to e of 1 plus I t xk over root n plus I t xk squared over n plus dot dot dot. Okay, and so we get the Taylor expansion from here. So what do we have here? We have 1 plus, oops, there's an IT squared I put there. We have 1 plus IT comes outside. Expectation of xk is 0. 0. That's why we take mean 0, so that we don't mess this up. 0. And then what do we have here? We have minus t squared over n times expectation of xk squared. But the expectation of xk squared minus mu squared is the variance. Mu is 0, so it's 1. And you can see where this is going. Something like this. You get the Taylor expansion of something like that. Okay, now you see immediately all of these terms are the same, because they're identically distributed. And I've got n terms. And you can see the same game as yesterday. That. Thus, phi Sn of t is equal to product 1 minus t squared over root over n. I think I forgot a 2 here. There's a 2 factorial. 2, sorry about that. 2 factorial. And as I think everybody sees what's going to happen here, it's to the nth power, and this converges to e to the minus t squared. So, which is the characteristic function of the normal. So I proved this too. So,
I mean, in so far you have not really use that it is identically distributed so much.
No,
as the- as
except
its
for the
mean is
variance
zero
and yeah,
variance is one.
yeah.
But probably will it create a problem because the O constant will start depending upon the random variable, or it will be hold true?
Oh,
it will
if
be
you
a
want to
bounded-
generalize it, you mean? If you
Yeah.
want to, no, it wouldn't be, as long as you assume some sort of boundedness on some parts, yeah. It's not terribly, yeah. And I'm gonna discuss variations of the central limit theorem, where the independence is assumed, but identically distributed is not. I'll talk about that in a second, yeah. Okay, so we have this, so this looks much easier than that. So it looks like a beautiful way to prove the central limit theorem, at least in the world of characteristic functions. You managed to do it just like that. And so now the question is, can I go from the world of characteristic function back to the level of distributions? And that's where this, as I said, I'm not going to give a course in probability theory, but this is what is called the Levee continuity theorem, to use a fancy word. So now we would like to deduce that Sn over root n tends to the normal. We only have it in the level of characteristic. So, to do that, there's a theorem of Levee. I'm not going to prove it. It's called Levee's continuity theorem. Basically says that if x1, x2 is a sequence, is any sequence, let's put any sequence of random variables. Any sequence of, they don't have to be independent, any sequence of random variables such that phi xn of t tends to phi of t for all t, for all t real. I don't think you need to really worry about it. It's enough to have it even on the small disk. Then there exists a random variable x such that phi x of t equals phi of t. That means that limit function is the characteristic function of a particular random variable. Okay? That's what I need. I need to get hold of a random variable of whose that thing is characteristic function. And if that's the case,
It's somewhat similar to this Weil-Secure distributions, or that space of continuous functions are dense.
yeah. There are lots of similarities, yeah. So you have this, and therefore you can deduce how do I get x from how do I get the density function from this? Well, you take the inverse transform, because remember the characteristic function is the Fourier transform of the density function. This is the Fourier transform of f sub x, right? And therefore, if I want to get my hands on f sub x, I take the inverse transform, and so I get my hands on the density function. So this is a general theorem, has nothing to do with independence or identically distributed. The general theorem of Levee. Now I take this theorem, I'm not going to prove it, and you apply it to what we just have here, because we have that, I erased it, but we have that phi Sn of t tends to the characteristic function of this, right? Therefore, and I know there that the characteristic function here is the characteristic function of the normal. I already have it. Therefore, this guy's got to tend, so I've got my distribution in my hand, Now I can take inverse transform and say, yes, it works in that case too. So now, applying this theorem, to our context, we see that, see, when we write this, in technically speaking, this is what's called weak convergence, technically speaking. So we're talking about in terms of the density function. So you integrate a function with these measures, it converges to the integral with that measure. Okay, that's what really is this. And therefore, we see that Sn over root n. Sometimes people write this, but I don't like the symbol because it looks like implies. I like this with a W, which is the weak convergence in terms of, if you give me in terms of density, probability density function, but this is a measure, these measures are converging to that measure, which means integral of f with these measures converges to the integral of f with this measure. That's what it means. That's the weak convergence. We'll write it this way rather than. I'm sorry, but there's all this confused notation in the literature. That's why you write your own books where you clean it out. Okay, so that's this now gives us that the central limit theorem also works in the case of discrete random variables. Because we move to the world of characteristic functions, we invoke this heavy-duty theorem, which allows us to get back and say it also works for discrete random variables. Okay, so if you've had a good solid course in probability theory, or you look at, somebody asked me for what books to read. Feller is still the classic, William Feller, Introduction to Probability Theory, volumes 1 and 2. I think this could be in volume 2. But anyway, it's all there. And the other problem with Feller is that it's some outdated notation. That's all. Okay. Now let's see if we can apply some of this stuff. Question?
By root n we should remove because you already changed the notation. Sn is x1 plus xn by root n already.
Oh, okay. Oh, was it? I'm sorry. Okay, that Sn I'm thinking of as just the sum of the xi's.
Yeah.
No, but we started and the other one.
Oh, did I? Okay.
Ah.
Okay. Okay. So yeah. If I use that notation in the notes, I'm sure you can clean it up. Yeah.
This theorem is saying that there exists a random variable x such that this happens. But do we need like xn should converge to x or something? I mean, are we using when we apply it to our context? How do we?
No, then what I'm saying is, once you have this, so phi xn of t converges to phi x of t, and what it would mean, therefore, once I have a random variable x in place, I can get hold of the density function by taking inverse Fourier transform.
Okay.
Okay, and then go back, taking inverse transforms of this allows me to tell that the density functions here converge to the density function here.
I see.
That's what this is. This statement really
Yeah.
is. Yes.
So this you can do from first step that Sn by root n, the characteristic function of Sn, phi of Sn, that is the Fourier transform of the density function. So from there you can apply inversion theorem to conclude that also.
Yes, I can, but these are discrete now. So I know you're mixing up the yesterday's lecture. Yesterday's lecture was the continuous case, and this will give you a new proof of the continuous case by what you're just saying. But you can't take the inverse transforms of these silly things. That's why you can take inverse transform of this, and then that will allow you to get the density function from the Okay, so I think so you do have to go through this route if you want to cover the discrete case.
So,
Yeah.
don't you already know the existence of an x just by looking at the right hand side?
In our case, yes. In our case, yes, because we're dealing with the normal. But in general, in the discrete case, when you have, I want to get I want to have a general theorem like this to conclude that I have this limit theorem, but I don't have it in the discrete case. In the discrete case, I only recognize when I go to the world of characteristic functions that it's this guy in the world of characteristic functions, but then I need to get a random variable of which it must be the target. That's basically where the problem lies. So now I guess if x1, xn, x1, x2, are identically distributed independent random variables which are discrete and mean 0, variance 1, then x1 plus x2 xn divided by root n tends to phi. So you see this is always weak convergence. This is not a limit as such. It's weak convergence in the sense of density functions. Yeah. So we really are talking about the density function. In other words, i.e. the probability, let's call this Sn, the probability that Sn is less than alpha tends to 1 over root 2 pi minus infinity to alpha e to the minus t squared over 2 dt. That's the theorem. We are talking about probabilities. Probabilities are density functions. It's not pointwise convergence. It's convergence in the weak sense that you integrate f against the measure, it'll tend to that thing. Often called weak convergence in literature. Okay. Now, let's try to apply this to some familiar discrete random variables that we are familiar with. Recall the Bernoulli distribution. So probability. Now here, this is where I have problems with this notation. The probability that x equals 1 usually is denoted by p, and the probability that x equals 0 is denoted by 1 minus p. But for me p is a prime. So we don't use that. So we'll use r. And in this Bernoulli situation, what's the expected value of x? Well, it only takes on two values. It takes on value 1 with probability r. It takes on the value 0 times 1 minus r. Expected value is nothing but r. And what's the variance of x? Well, the variance of x is e of x squared minus the mean squared. Well, e of x squared is the same as e of x. This is an interesting thing, isn't it? This silly thing takes only values 0 and 1. When I square it, it's still the same thing. So, fortunately, this is nothing but r minus r squared, which is r times 1 minus r. You must have seen this. It's a basic course. The Bernoulli distribution has these as the mean and the variance. Okay. This is where it all started, of course. The Bernoulli distribution coming from coin tossing, right? So, and those guys in the 17th century, and ended up getting the central limit theorem, some version of it, not the full version. With great difficulty, so. So suppose now that x1, x2 are independent and distributed Bernoulli trials. Bernoulli trials or Bernoulli random variables. Then Sn, put Sn equal to x1 plus x2. Then Sn counts the number of successes in n trials. The number of successes, so probability that Sn equals k is given by, in n trials, you've got 0, 1, 0, 1. How many ones am I going to get? I get, if I say, if I have, it's going to be n choose k, times r to the k, minus r to the k.
Will be n minus k.
N minus k, thank you. Yes, n minus k. Yeah. Right, the probability that Sn equals k is simply that. Now, these are independent random variables. They're all identically distributed. They have mean r and variance r times 1 minus r. And so, because they're independent, we see the expectation of Sn equals the expectation of all of those, which is simply n times r. The variance of Sn equals, well, sum of the variances, n times r, 1 minus r. So by the central limit theorem, we see that probability Sn minus nr divided by square root nr 1 minus r, oops, alpha, tends to that. Fair enough? Okay. But what does this mean? I.e., probability that, or put PR there, probability that nr minus, let's see, probability that, if you don't mind, I'm just going to do this. Put beta there, and put alpha here. I'm just going to do that. Okay, good. Then what do we have? We have probability nr plus alpha square root nr 1 minus r less than Sn is less than or equal to nr, sorry, beta, yeah, nr plus beta root nr 1 minus r tends to probability that Sn equals k is this. So I'm going to count for each k in this range, I get the following theorem. So this is the theorem proved in a very complicated manner. This is what I always find interesting. This theorem was proved in 1812 when that stupid war was going on. You learn your history, you'll always learn about these wars and things. The War of 1812, but nobody ever teaches you that this was happening in 1812, which is far more interesting, right? So now we get this remarkable theorem, summation k. So we have Sn equals k, if k lies between these two things, so k minus nr, so k lies in that range. Let me just put a dash, okay? K lies in that range. The probability that this happens is r to the k, 1 minus r, k minus k. This tends to phi of v. So the dash means that k is in a restricted range, that nr plus alpha square root nr 1 minus r is less than k nr plus beta square root nr 1 minus r. Very interesting because it's not. If it was the full binomial sum, you have, of course, 1. It's the full binomial sum. But it's not the full binomial sum. It's a binomial sum centered around these points. The interesting thing is, if you specialize to a fair coin, in a fair coin, the probability of heads is a half. So r equals a half. Specializing. So r equals 1/2. We get that in that case, r is a half, this is a half. We get 1 over 2 n summation of, keep this n k, k in this restricted range. What is the restricted range? Well, k, n over 2 plus alpha square root, well, r is a half, 1 minus a half, that's a quarter. Square root of a quarter is 1/2. So square root of n over 2. In other words, you're hovering near the middle coefficient. This binomial coefficient, the largest one is in the middle coefficient. And if you move to the left of that middle coefficient by order of square root n, or move to the right by order of square root of n, you have an asymptotic. Pieces of the binomial expansion. All the action you know is taking place probably near the middle. In n tosses, you'd expect 1/2 of them to be heads. Well, what is the probability that it actually is the case? That's what this is calculating. And the standard deviation is of the order root n. So you get this, I mean, you can't prove these theorems without this. You can try, I mean, if you put factorials in, and which was what Demars was doing. He put factorials in, and it was a mess. He was trying to use Stirling approximation, and he tortuously ended up getting this with a lot of work. It's interesting that Stirling's formula actually arose in this context, because he needed to know how these factorials behaved. Which is kind of resonant with our, even with the Bertrand postulate calculation for the factorial, how does this behave? So you get something very neat like this, which I as far as I'm aware, I don't know how to get without using this. So this is one application. This is Demars Theorem. This is actually how some intuition that the central limit theorem is probably existing. So they found the central limit theorem in the case of Bernoulli trials as a special case. Yeah. Now let me try to impress upon you the second result. Of Ramanujan, which I always find fascinating. If you take the sum n to the k over k factorial, k going from 0 to infinity, you will get e to the n. But let's take only k going from 0 to n. And how does it differ from e to the n? Well, Ramanujan showed it only picks up half of each. So if you took the sum from k equals 0 to n, instead of k equals 0 to infinity, you only get 1/2 of. I thought that's kind of cute. Right? And if you have a copy of the collected papers of Ramanujan at the very end, it's in this question session. He submitted quite a number of questions and solutions to Math Student, yeah. By the way, here's another, so I'm one of the editors of Math Student, so here's a pitch. Please submit interesting problems that you come across. I mean, you can't copy problems, but you might make up new problems for solution. Okay? And I would really like to see a vibrant problem session in Mathematics Student, something like the American Math Monthly problem sessions. So please, I know that anyone who does research comes across some interesting questions which you may want to put into some sort of challenge form and then submit along with your solution. We can have some sort of exchange, academic exchange, and well, it should be around the world, but it probably won't be. But at least in India we can have it and do that. Anyway, that's the Math Student session. He, I think, did he pose this question or did he answer the question? I think he posed it, and there weren't any submissions, and he finally answered it, and it was hard duty analysis, heavy duty analysis that he used in order to prove this. So he certainly was not aware of the central limit theorem. He certainly didn't use any probability theory. But it is an interesting result, and people have written papers on this limit, and people have written papers on generalizing this stuff. All of those papers are trivial consequences of the central limit theorem. Okay, so let's see how. You can guess what's going to happen. It's the Poisson distribution. Yeah, exactly. You got it. So the Poisson distribution is obviously the thing to look at and ask oneself. In the case of the previous example, we took the Bernoulli trials and added up independent Bernoulli trials and got this nice result about binomial coefficients. Now we take independent Poisson variables and see what you get. See what you get? Well, you get this. Very interesting stuff. Okay. Preliminary facts. also the Poisson distribution. Probability that x equals k is given by e to the minus alpha, alpha to the k, or k factorial. Okay, so this is what's called the Poisson distribution with parameter alpha. And I want to kind of introduce some notation. If x is a Poisson variable with parameter alpha, and y is a Poisson variable with parameter beta, then x plus y is Poisson variable with alpha plus beta. This kind of wants to go back to this business of algebra of distributions that I'm talking about. Similar thing happens with normal. If you have a normal distribution with mean mu and variance sigma, and so if x is a normal distribution with these parameters mu and sigma, and y is normal with mu prime and sigma prime, then x plus y turns out to be normal with mu plus mu prime, sigma plus exercise. So these are the, I mean, there has to be some sort of nice algebra to codify these things, because I'm sure when you learnt it in a probability course, they didn't mean anything. There was no structure. It was an ad hoc. You had this Poisson, you had normal, you had Bernoulli, binomial distributions. It didn't really, there was no unifying thread. But anyway, you have this. I'm just going to leave this as an exercise. Now, so suppose x1, x2 are Poisson random variables, independent Poisson random variables with parameter 1. So maybe with my notation are Poisson of 1, my notation. Then x1 is x2, xn is Poisson. One more point. You have to calculate the mean. So I shove this in the exercise as well. The mean of Poisson alpha is alpha. The variance of Poisson alpha, x is also alpha. So these are all exercises, okay? Do this, and do this. It's very simple and straightforward. So, once we have this knowledge about the Poisson distribution, then we have this fact. We have the, let's call this Sn, the expected value Sn. So each of these is 1. Expected value is n. And the variance, independence, right? The variance is, some of the variances here is also 1 plus 1 plus 1, n. Therefore, I can apply central limit theorem. COT implies probability of Sn minus n over square root of n is less than equal to alpha. N is 2. nice theorem for free. But for free. Now, let's choose alpha equals 0. Then what's phi of 0? 1/2, exactly. Therefore, probability Sn minus n less than divided by root n is less than equal to 0 tends to 1/2 as n tends to infinity. Well, what is this? Same thing as probability. This is the same thing as probability of Sn less than or equal to. So this root n goes away, it's n. But the sum of Poisson is again Poisson. And so the fact, sort of the notation, but this is nothing but summation k going from 1 to n, probability of Sn equals k. Is it not? Sn is less than or equal to n. If these are the values it takes. Therefore, well, maybe I should start at 0 because the table starts at 0. But this is now nothing but, it's a Poisson random variable, e to the minus n, n to the k, over k factorial. Tends to a half. So it's interesting that Ramanujan was doing this in the early 1900s. Before really central limit theorem was really a powerful topic for research. Is there a class in here, by any chance? I see a lot of people. Is there something going on? No? Okay, so you get something really neat. There are more things to be said, but I won't say them. And it's interesting that there is a connection between these types of theorems, limits, and the Hardy-Ramanujan paper. There is a connection, because these sums do appear. And I'm assuming that Ramanujan was very familiar with that, and he's the one that put those things in. So, okay, now I'm running out of time very quickly. So far, some neat applications. Other things are there, like, for example, there's a cute way of deducing the Stirling formula for n factorial from this. But that's like using a sledgehammer to do something very simple. In my opinion, Stirling formula is not complicated. It can be done much simpler. You don't need central limit theorem to deduce that. Okay, so these are some interesting things. Now let me get back to the situation with respect to the Hardy-Ramanujan theorem and the Erdős-Katz situation. The Erdős-Katz theorem. So we will use so let for each prime p, let maybe I may run out of time, so I might continue some of this stuff tomorrow, but so let me get started anyway. For each prime p, let xp be the random variable with xp, probability of xp equal to 1 to be 1 over p. 0 being 1 minus 1 over. So this is a Bernoulli random variable on the natural numbers. How would you do this? Well, you could just take all the multiples of p, call that set A, and the complement is b. If it lies in A, it's 1 over p. If it lies in B, it's 1 minus 1. So there is a way to realize this. It's a Bernoulli random variable. Okay, these are independent random. These are independent. These are independent random variables. But they're not identically distributed. Why not? Well, if they were all identically distributed, they'll have the same mean and the same variance. Well, what's the mean? The expected value of xp is, well, it only takes on two values. One was probably 1 over p, and 0 with that thing. So 1 times 1 over p plus 0 times 1 minus 1 over p, so it's 1 over p. Variance of xp is the expectation of xp squared minus 1 over p squared. But the expectation of xp squared, well, let me write everything down. Xp squared, as we discussed earlier, is the same as xp. So it's 1 over p, 1 minus 1 over p. So if they were all identically distributed, they'll all have the same value, but they don't. So the romantic idea, I keep saying research begins with romance, right? The romantic idea of trying to apply central limit theorem to this thing and trying to get the Harish-Chandra theorem didn't occur until the 1970s. We find this very counterintuitive. And it was an idea of Billingsley. Didn't occur until then. Because of this problem. Couldn't really use it. But Billingsley actually was, I think he left math and became an actor. I guess he was somewhat of a romantic. So he actually made this work. And you make this work by invoking a very interesting theorem, which I'm not going to prove, called the Lindeberg-Feller theorem. By the way, I have a colloquium style slide talk on the history of the central limit theorem. So I don't know whether to give it in this classroom or a separate session, which may be accessible to a wider audience. So if you think in the course of the one more week I'm here, right? If you think there's interest in the colloquium style talk, I can put that down. That many of you will be able to follow the history. It's got pictures and no heavy-duty math really in that thing. And the Lindeberg-Feller theorem is what we need. So let me try to explain the Lindeberg-Feller business. It's interesting because all this stuff was going on in different worlds, as I said, the world of probability theory. And because people don't pay attention to what's going on in other fields, things don't get discovered. And sometimes people keep reinventing the wheel in different disguises. So these are not identically distributed. Lindeberg and Feller, I'm not sure, maybe 1938 or 1940s or something like that. It's interesting because 1738 or thereabouts is when Demars starts doing the coin tossing. And 1938 or thereabout, 200 years later, is when the Lindeberg-Feller theorem shows up, finishing the entire history of, kind of putting the final touch on the central limit theorem. And the condition is the following. Suppose I have independent random variables. Let's say mean yeah, let's say mean 0. You can, by the way, I told you this business of you can always take the thing and subtract the mean, make sure everybody's got mean 0. And with distributions, let's call them f1 of x, f2 of x, dot dot dot, respectively. One of my students keeps saying, respectfully. So we have these distributions. Then let the variance of xi be sigma I squared. Put Sn squared to be summation sigma I squared, I going from 1 to n. Then if we have the condition star, limit n goes to infinity, 1 over Sn squared, summation k going from 1 to n, integral absolute value epsilon Sn y squared fk of y dy. So this is for every epsilon positive, we have this limit equals 0, then x1 plus xn divided by Sn has the normal distribution. Tends to the normal distribution. Tends to 5. So weakly tends to 5. Which is the central limit here. So you've managed to get rid of identically distributed things and replaced it with what's called the Lindeberg-Feller condition. Okay, this is often called the Lindeberg-Feller condition. So you have this technical condition, then it's fine. Now let me just get rid of this technicality here, okay? Suppose that my random variables are bounded. Like here. The values are 0 or 1. They're bounded. Suppose they're bounded. Suppose that Sn tends to infinity. Okay? If Sn is tending to infinity, and what is this? This is the density when y is bigger than something, and that's the density that xk equals y. But y is bigger than, so Sn is tending to infinity, so this is huge already, outside the range. Therefore, this is an empty sum. So if the random variables are bounded, this condition is satisfied. As long as Sn tends to infinity. So remark, that's why I'm thinking that I don't want to rush the Erdős-Katz business, but maybe I can set it up and continue tomorrow.
Can you please repeat that argument?
Yeah. So if my random variables are bounded, and if S sub n is tending to infinity, then this can be taken to be humongous, outside the range of the values of the random variables.
Well,
Then
n is sufficiently
Yeah.
and it's sufficiently large, there's nothing to do.
So that, yeah.
it's
the integral will.
V0.
Yeah,
So remark is that if the random variables xi's are bounded and Sn is tending to infinity, then the star is satisfied. And therefore, in that case, as long as Sn is tending to infinity, you've got the central limit theorem. Fair enough? Now, in this case, therefore,
Is it clear
Where-
also from the, means, what I mean, if suppose they would have been identically distributed, then this condition is satisfied, is it?
if they're all identically distributed, it's probably satisfied. I didn't check that.
Yeah, because I think we'll have 1 by n times the variance.
The
square.
same thing.
Yeah.
Yeah. And the variance is already finite, therefore this is the tail. It's a tail of a variance. I think, yeah. So you can get the classical central limit theorem. That's basically what your point is. Yeah, you can probably get that. So this is it. By the way, the central limit theorem. There's a theorem somewhere. I have to check it, but more or less, this is an if and only if. This guy tends to the normal if and only if this condition is satisfied. So this is the final crowning, the cherry on the dessert or whatever of the central limit theorem.
Found a condition.
This is the condition. This is the condition that 200 years it took. That's why I like to give this colloquium with the slides. Should be accessible for everybody, but it's a big deal. Somebody had a question? Okay. So now let's go back in this context. What do we have here? What is the variance? What is the variance? Well, the variance of xp is this. And so we have to calculate Sn squared equals p less than n, let's say. Let's not worry about the indexing, okay? It's not, I'm changing my indexing. It's not, I'm not doing x1 plus x2 to xn. I'm just basing summation xp, p less than n, okay? So don't worry about it too much, this indexing. So this guy is, so the variance that is going to be, in each case, it's going to be 1 over p, 1 minus 1 over p. But this fair enough? This is all 1. This is bounded, converges, summation 1 over n squared converges, so that's all 1. But this is log n from our previous lectures. Hey, it tends to infinity. Therefore, we can happily, I can't believe that this observation was not made until the 1970s. Billingsley made it. So once I'm sure he was on cloud 9 when he got the idea, kind of spiritual epiphany or something. And then he realized he could make it tick. That's it. Once you went through this obstacle that's not, identically distributed business, and you've got a way of getting out of it, it should work. You should now be able to write down the thing. There's only one more problem, and I think when I highlight the problems, I think it's good to place to stop. Everything is set up, and I'll continue tomorrow. And this way you have the strategy to understand what's going to happen tomorrow. So we can apply to summation xp and deduce what? Let's call this Sn. Deduce what? Well, deduce that we have to subtract off of 1 over p to make mean 0. To deduce that summation p less than n xp minus 1 p divided by square root divided by Sn, because that's the theorem. Theorem says Sn square root of this thing. Square root of what? There could be an old one, but let's not worry about that. Tens weekly to the normal, and it's looking like summation x. So this 1 over p is like log n, and you think xp of n, what does it do? It spits out a 1 when p divides n, and spits out 0 when p does not divide n. Therefore, it looks as if we're going to be pretty close to getting the omega of any number, but that's not quite the case. So we certainly have this, but is this well, what is the Harish-Chandra theorem? So it's that probability of omega n minus 1 log n divided by square root log n. Alpha tends to 5. That's the Harish-Chandra theorem. But the Harish-Chandra theorem is doing the funny thing. It's taking the collection. Let me put an M here, if you don't mind. Let's do this. Okay, put an M there. And what is it doing? It's taking the interval from 1 to n, counting the number of m's that satisfy this, finding the proportion, and then saying the limit is going to this. So this is really a probability measure on the first natural numbers, yeah. Where p sub n is the probability measure on 1 to n, the point probability measure on 1 to n. So it's 0 inside. So we have a situation where, on one hand, we have the natural numbers here as the sample space, and on the other hand, in each case here, we have different sample spaces, different measure spaces, 1 and 1 to n. So we have to worry about how to go around this changing of routine. So there's a nice approximation trick that, let me just write something down and stop. Oops, this is not here. So the XP's are random variables on the whole set of natural numbers. If p divides n, it's 1, 0 otherwise. But here, on 1 to n, we define yp of n, yp of n equal 1 if p divides m, 0 otherwise. And then we see that summation p less than n yp of m is equal to what? Well, it's equal to, it's going to be 1 only when P divides M. P less than N, P divides M. Oh, sorry, this should have been M here. Should have been M. We look at, for a fixed P, we look at this and we see that this has got to be N over P. And yeah. So the way to count, we may want to say that the probability of yp equals 1 is then what? The probability of yp equals 1 is this number divided by n. The usual counting process, correct? Yp equals 1 over n, n over p. Okay, so this, if I didn't have the square brackets, it's 1 over p, which is imitating xp. But yp doesn't quite imitate xp. It imitates xp with an error term of 1 over n. So Billingsley's strategy is to say that I've got my central limit theorem for xp, and I want to get the central limit theorem really for yp, and I'll get the Harish-Chandra theorem. But the yp's have messy behavior, and so we will play the moment game, what's called the method of moments. So if I want to determine what is the distribution of the yp, because that's the real function, and if I can show that the yp's have the same moment distribution as the normal, then I'd like to say they're normally distributed. Okay, so that's the strategy. I'm going to come to that, I think, tomorrow. I'll set it up in more detail. But you see that once you have the romantic idea of trying to apply the central limit theorem to get the Harish-Chandra theorem, a lot of things actually come into play very neatly. And if you look at the original paper of Erdős and Katz, you'll see that it's heavy-duty sieve theory. The Brunn sieve is used left and right. And it is actually a messy paper, complicated paper. This is actually very simple. Billingsley's proof appeared in the American Math Monthly in the late 1970s. So he thought it was that simple that he could explain it to undergraduates. So I'll take that up maybe next time.
Whenever we are writing P, we will mean this probability measure on 1 to n, right?
Yeah, yeah, it should be piece of n, you're right. So then I'm going to take a limit as n goes to infinity of these measures. So the spaces are changing. Yeah, and the interesting thing in that Levee continuity theorem also, those xi's are random variables on different spaces. But then you have the characteristic function as a function of t. And the spaces are gone. And then you're showing that the characteristic function tends to the normal, or whatever. And then there's a universal distribution somewhere. So there's a lot of stuff that helps putting everything together in the end. But you needed to know probability theory and number theory together in order to put this together. Any other questions?
The YPs are not really independent.
No, they're not independent either. They're not independent, they're not, nothing, there's nothing. But they look like they are. They are almost independent. They're almost independent. That's
PI is less than, PIs have to be
yeah.
less than square root n.
Something like that, yes, exactly. And this is, by the way, this whole business of approximating, trying to make things independent, later on becomes what's called a theory of mixing. So you try and say the probability of A intersect B, and you want to say it should be equal to probability of A times probability of B, but you take the difference and you put an error estimate on it and then continue. And this is often referred to as mixing theory.
Is it same as mixing from ergodic theory?
Yeah, same thing, exactly same thing. See, there are all these different worlds using different terminologies. Ergodic theory is also part of the same type of probabilistic worldview, right? So.